All right, so today the reading for this week was examples of products. So chapter 2, section 5. Yeah. Did anybody read that? No?
I did not, sorry.
Okay. This is a great reading group. Nobody reads the book. Well, okay.
I'll give you some good news. The guy that I worked with at my last job who started our AWODI reading group just applied to Takt.
Oh, awesome.
Nice. Maybe he'll read the book.
Fantastic. Maybe we can reboot the reading group and then he can lead it.
He was taking it at a much faster pace before. I actually like the pace we're going at better, even though I've been a little bit spotty in my following.
Yeah. Does anybody think that the pace is too slow?
I don't.
Or like too detailed, maybe?
No, I think this is really, really good. I think I'm getting more out of it.
Yeah, I think for me as well, I'm getting more out of reading the book in this much detail, you know?
Yeah.
Really figuring it out. Okay. So examples of products, right? So page 41 in my copy of the book. I will share my screen so that we can all look at the same thing. I made some notes on the weekend. So when I normally do this reading, I usually spend like a couple hours in the evenings, like Saturday, Sunday, doing this. So, you know, it's like 4 hours out of my week that this is taking. Anyway, so category theory, examples of categories. So the first example we've already looked at is the Cartesian products of sets. Right, so we saw the product A comma B, you know, which is the pair type of the two types A and B, where an element of that type is just a pair, one of type A and another one of type B. But we could have also used the pair, you know, B comma A, right? It's also a product of A and B. We could also use, you know, unit to A comma B. That's also a product of A and B. We saw that we could use this sort of church encoding. So we could say like, okay, if I have a function that can receive both an A and a B and turn that into an R, then I can turn this whole thing into an R, right? So a value of this type really consists of a value of type A and a value of type B. So this is the sort of lambda calculus way of encoding a pair.
And what was it? Someone was just posted in one of those blog posts about algebraic data types, and that kind of matches up with the algebraic data type, you know, number of inhabitants of A comma B, right?
Yes, that's right. So there are B times A inhabitants of this type, and of this type, and also of this one.
And of that type, yeah.
Yeah. So there are B times A, and this is power. So there are A times B to the power of 1
Right.
things in here. But if this were bool, now there are, you know, a power of 2 more inhabitants.
Yep.
Okay, so yeah, all of these are isomorphic to one another. We can write functions, you know, back and forth, and they're all the same in that abstract sense. So what he goes on to talk about products of structured sets. So for example, the product of two monoids M and N. And that's really straightforward. We really just take the product of the underlying sets, and then we do the laws or the structure over those sets. We do that element wise on the two different sets. For example, a product of a monoid, we just have a pair. One side is M and the other one is N, where both of those types M and N are monoids. And then the mempty of the product monoid is just the two mempties together. And then mappend on products is just mappend on the components of the product, right? And this works for groups and rings and fields, and no, actually not for fields, not necessarily. But yeah, it works for structured sets in general.
What is it about fields that makes it not work that groups and rings don't have that makes it work?
There's something about there's something about division. I'm not really sure.
Okay. Division, yeah, that's a good enough answer for me.
Yeah. So it works for groups, so with inverses and all that stuff. But for some reason, I haven't actually studied. It doesn't work for all fields. Okay, we can take products of categories. Huzzah! So taking a product of two monoids is a special case of that. Those are just categories with one object each. And so then we take the product of those monoids, and now we have a product of categories. But we can take products of categories in general. So in that category cat of small categories, there is then a product category. So if we have two categories C and D, there's a product category C cross D. And it has these two forgetful functors, or the projections into the two elements of the product. So one functor to C and the other one to D. We can call those functors P1 and P2, or first and second. And Awodi calls on us to show that the universal mapping property holds for the product. That is stated as follows. So for all small categories C and D, and any other category X, with functors from X to C and a functor from X to D, right? So these two functors, X1 and X2. So you can see that this is sort of a diagram with three categories. There's a category X in the middle, and it has two arrows going out to the category C and D. And there's a unique functor U, which goes from X to the product of C and D. So that's the one that goes, down in the triangle, such that, the composition of P1 and U is X1 and P2 and U is X2. That is, it makes that sort of triangle commute on, which was on, the bottom of page 39. So the situation is very much like that on the bottom of page 39, except that X, P, A, and B are all categories, and P is, A cross B, the product category of A and B. So there's some unique functor U from, any X, which has these two functors X1 and X2, into the product category P, or A cross B. So we have to show that holds. The approach I took to show that holds is just to show that this holds for categories in Haskell. So we have this class, a type class category. So C is a category if it has an associative composition operator, like this. So we take a C, which is an arrow from Y to Z, an arrow from X to Y, and an arrow from X to Z. And we have an identity arrow from X to X, which is supposed to be a unit for this composition operator. And then we have this product type, which just has these two projections, P1 and P2, goes from the product of C and D of A and B. So this is an arrow in the product category C and D between the objects A and B. So there's an arrow from A and B, and an arrow, an arrow in C between A and B, and an arrow in D from A to B. So then the product of these two categories, C and D, we can come up with a category for the product of C and D, where the composition of the two arrows in the product is just the product of the composition of the two sides, right? So it's exactly the same situation as with the monoid, except it's sort of more generalized to other categories, right? So the identity of the product category is just really the pair of the identities, or the sort of the ordered pair of the identities, and the composition on the products of the arrows is just the composition on the arrows that are in that product, right? So that's pretty straightforward. And then I have this type here, which is a natural transformation on the arrows. So this should go from oh wait, so I guess this is a functor, yeah. So a functor from C to D will take all arrows in C from A to B to an arrow in D from A to B, right? So then I'm saying that given a category X and a functor from X to C and a functor from X to D, right? So the top of that triangle, I have a unique functor from X to the product of C and D. And that's just, well, apply x1 to F and apply x2 to F, where F is the arrow in X, right? So given some arrow in X, I can put that in C, and I can put that arrow into D, and then I just take those two and I stick them in a pair, and now I have an arrow in the product of C and D. Easy. So in English, that states that the functor U simply takes every morphism F in X, in the category X, to the morphism x1 of F paired with x2 of F. There's these two functors. So F sent across those two functors to the category C and D. And then it takes every object X in X to the object under these two functors pairwise. And then these things hold. That is it makes the product diagram commute that U is in this relationship with P1 and P2, and I sort of show that here. So if P1 composed with U is X1, then then we'll just substitute in the definition of this sort of this make U. So this is the U, X to product CD at the end here. So make U takes these two functors here. So P1 composed with U is P1 of, what the definition of U, which is make U of X1, X2, and whatever F was. And the definition of that is, well, it's X1 of F. And then the P1 of the, sorry, I substitute in the definition of make U here, which is, well, it's product of X1 of F and whatever. And that's P1 of that is going to be X1 of F. Yes. So X1 of F is X1 of F. And so that proves that this exists and that it has the properties that we want. Great. So that's existence. The second half of showing the universal mapping property is to show that this morphism or this functor U is unique. So we just have to show that given any two such functors, they are the same. Okay, so given that P1 composed U is X1 and P2 composed U is X2, and given that we know that P1 just takes the left half of our ordered pair, right? So it just projects out the C part of the pair, C and D. Then U would have to assign that very same morphism or object in C that X1 does, right? So, there's no way that we could choose a different morphism in C than what we already chosen with X1. So therefore, this is the only implementation that actually works. Like there's no way in this definition here. So if we look at make u, there's no way that we could choose a different object under f. Then, like, if we can't choose a different c, and it's given by this functor. Like there's no other way of getting an object or a morphism in C, right? So therefore, any two definitions of this must be the same. So there's only one such functor. So then he goes on to ask to check that the products in posets and monoid are just the products in cat. That is, if we consider the categories of posets and we consider the categories of monoids, that the products in those categories are really just exactly the same as, the product of posets considered as categories and monoids considered as categories. And I've not done the work to actually show that. I think that's sort of trivial. I kind of show it up above here, that the the product of two monoids is pairwise like this. Yeah, so since in the category of small categories, composition is just component-wise, that it's just on the pairs. These proofs I don't think they're very interesting. So the functors between different posets are monotone functions. Then functors between ordered pairs of posets are pairs of monotone functions. And likewise, if functors between monoids are monoid homomorphisms, then functors between pairs of monoids are pairs of monoid homomorphisms. Okay. More interesting is the product in posets. So if we consider a poset to be a category, remember that a poset forms a category where there's an arrow between two objects, A and B, if A is less than or equal to B, right? So a poset is just a set with this inequality or this comparison relationship. So we can compare two objects. So if we can compare two objects A and B, and A is less than or equal to B, then there is an arrow between A and B. And so the product of two objects in this category is their greatest lower bound, which is sort of interesting. So it's some element P, which is, between A and B. So we can see that, there's an arrow from P to A and an arrow from P to B. So that looks like our sort of the bottom of our product diagram. And then for any other element X, that has the same shape of diagram, X in the middle and arrows out to A and B, which is sort of the top of that triangle, then there's a unique arrow that goes from X to P, which goes down the triangle. And that's just the fact that X must be less than or equal to P. Right, so that means we can see that, there's some P that is between A and B, and such that for every other X that is also between A and B, sorry, it's not between them. It's less than both A and B, less than or equal to both A and B. Right? So P is less than or equal to both A and B, and X is less than or equal to both A and B, and X is less than or equal to P, and all such X are less than or equal to P, then P must be the greatest lower bound of A and B, right?
Wait, isn't that an upper bound or? Yeah.
Oh, it's the lower bound of C because it's below both A and B.
Oh, okay, gotcha.
And X is below both A and B.
Gotcha.
The comparison of the two lower bounds is such that P is greater than all X. So it's the greatest upper bound. The greatest lower bound. Yeah, if we flip all the arrows, then we have the least upper bound.
Right.
Okay. Others that I thought would be interesting to look at, I don't think that he actually goes into these in the book. So he goes on to looking into like, okay, for those who know about topological spaces, which I don't, but if any of you guys do, and you can explain example 5, I mean, I can sort of work it out that like, okay, a topological space is like, you know, a neighborhood of open sets. And so, yeah, there's like a product of open sets is like the open set of their products. But like, I don't really follow this reasoning. Just not used to thinking of like inverses of functions and open sets, and yeah, so don't really have a background in topology or enough of an understanding of topology. So I thought we'd look at some other examples. So categories we've seen already, the rel, the category of relations. So then the objects are sets in rel, right? And an arrow from A to B between sets A and B is a binary relation R, such that it's all pairs of A and B, such that A is in A and B is in B, right? So it's basically, you know, an arrow is just like the set of tuples that come from the two sets. Okay, so sets of pairs. And then composition on these arrows, so the arrow S and R is the pair, all pairs A and C, such that for some B in the set B, and an A, sorry. Yeah, okay, so R is a set of A's and B's, and S is a set of B's and C's, and there's a composition of those two relations if there is a B in the set B that connects them together, right? So there must exist some B such that A and B is in the relation R and B and C is in the relation S, right? That makes A and C be in the composite relation S and R, right? So this is just relational join. And then there's the identity arrow, which is all pairs of A and A from a single set A. Great. So this is just from chapter 1. So then what is a product of two such sets? And it's actually kind of weird. So it must be a set P equipped with these two relations. P1, which must be a subset of the Cartesian product of P and B. And P2 must be a subset of the Cartesian product of P and A. That is, you know, it's an arrow from P to B and an arrow from P to A. But it must hold that for any other set X, and these relations from X to A and relations from X to B, X1 and X2, there must exist a unique relation U, which makes that whole thing hold. You know, that P1 composed with U and X2, I mean, and P2 composed with U is X2, right? So what it turns out is that the product is the disjoint union of A and B, that it's either A or B. So it's that set where the elements of the disjoint union are all the elements from A and all the elements from B that remembers whether that element is from A or B. So it's the same as like the Haskell either type. So it's either A or B, and it has that tag that says whether it came from the left or it came from the right. Right. So it turns out that makes this whole thing work, because I mean, we can see that, you know, there are these projections, there, you know, if my set P contains all the elements from B, then there is this this relationship, right? And if my set P contains all the elements from A, right? But that also makes all of this work because there's definitely going to be this composition, because you're always going to be able to find a value of type A that connects P1 and U, right? Because all of the A's are in there. And then same with this side, you're always going to be able to find an element of type B that makes this work, because all of the B's are in P. Great. Also looked at products in a database schema. So we're thinking of relations, like the category of relations. But if we look at a schema of relations, like a database, as a category in its own right. So a database schema, and this comes from functorial data migrations by Spivak. So database schema, and then is a category with relations. We call these tables. So those are the objects of the category. And then the arrows of the category are foreign keys between those tables. All right, so there's an arrow from the table T to T1 to the table T2 if there is a foreign key from T1 to T2. And composition of foreign keys is by considering the join path from one relation to another. So we follow the foreign keys transitively, right? So, we go from, order to line item to product. So there's an arrow from order to product by going through the line item, right?
How does this relate to the previous one, products in rel?
Well, how does it relate?
They seem very similar.
They seem similar, except so in rel we're considering the category of relations, right? Where the yeah, I guess it's pretty similar. The categories of relations is the so each object in that category is a relation, yeah. And then in a database schema, a category.
No. Each object in that category is a set.
No, yeah, sorry. Yes.
Or no. Excuse me. That's not the product category. That's rel. Rel is sets. My bad.
Yeah. So the objects. Sorry. Yeah. The objects in rel are sets, and the arrows are relations. And then once we go to a database schema, the objects are now relations, and the arrows are relationships among the relations. So foreign keys.
Ah, okay. Interesting.
So then a product of the two relations R1 and R2 is some table or relation P that has a foreign key to both R1 and R2. Right, so we can think of some table that points that has two columns. One of them is a foreign key to R1 and the other one is a foreign key to R2. But it has to be in such a way that for any other relation X with foreign keys also to both R1 and R2, that table X also has a foreign key to P, right? And so it must make this work, that joining R1 and X results in the same records from R1 as joining R1, X, and P. And then R2 and X joined have the same records from R1, R2, as joining R2, X, and P. So P has, the only option is that P has only the common columns of R1 and R2 populated with all the data from R1 and all the data from R2, right? So it's sort of similar where in the disjoint union where we had all the elements of A and B, right? So in the product of these two tables, we have all the rows from both of these tables. Except we only have the columns that are necessary to satisfy this product. Does that make sense? So it's like a join table. Okay. Just for fun, I was looking at just like a little category, the category of dominoes, right? So the game of dominoes actually forms a category, right? So if we think of the tiles of in dominoes, right? They have these faces, and they're this set, right? They're numbered from 1 to 6. And each tile is a pair, of A and B, of two tiles. I mean, of two numbers. And we can only compose two dominoes if the ends agree, right? So if we have a tile AB and a tile BC, we can compose that into a skeleton. This is the what is called in dominoes, with an A on one end and a C on the other end. And then we can compose further dominoes on the ends, right? That's kind of fun.
Does this form a category? I guess it does.
Yeah, it does sort of. It's basically the same one as the rel category. Right, except these are single element sets. 1, 2, 3, 4, 5, and 6. They all have only one element.
Right.
And there's an arrow. Yeah. All these arrows exist. So there's an arrow from every tile to every other.
Uh-huh.
But it turns out in the game of dominoes, there's actually one additional tile, and that's, there's one additional end, and that's the blank end. And that actually turns out to be the product in that category. This is kind of
the blank end can be combined with anything?
Yes. Yeah. So it's an arrow. At least I think this is the product, and so it's an object in this category, such that it has, for any two other. Sorry. So given two objects in this category, A and B, like let's say 2 and 3 or whatever, there's an arrow into. There's an arrow to them out of the product, right? That is, there exists a tile with that thing on the end, and the other, that goes out to the other one, right? So there are two tiles, P1 and P2, that go out of the product, right? Such that for any other X, we have an arrow into that product, right? And so I want to say that that is the disjoint union from rel. That is, it's all the elements from 2 and all the elements from 3. That is, it's both 2 and 3. So it will compose with either 2 or 3, and that holds for any two elements that we want to choose from this list. The blank will compose with either one of them.
So the product is the blank or the domino with a blank on both sides?
I think that the product is just the blank. And so if we take, so let's say that the blank is the product of 2 and 3, right? Then we have projections from the blank into whatever. Like we can put any domino basically on there to get an arrow into like 2 or 3, right? So those are. Oh wait, do those need to be unique? Do P1 and P2 need to be unique? I'm not sure that they do. I think we just have like multiple products. So there's one for each tile basically that you might want to be able to put onto the end of the blank. And but there's definitely a unique one from each one of these 1, 2, 3, 4, 5, 6 and blank. There's a unique arrow into it, which is the tile that has the tile that has, you know, one on one end and the blank on the other, or two on one end and a blank on the other, right? I think that it works out that way. Or maybe it doesn't. Maybe those are actually not unique. Because like you could go 2, 3, and then 3, 4, and then 4, 5, and then 5 blank. And like, is that the same? It's just like 2 blank? I don't know. So maybe this actually doesn't have products. I don't know. It's something to think about. Yeah, and then I was looking into, well, are there products and categories of window functors? And yeah, that actually turns out to be super boring. It's just like compose FG equals it's just that. Like the product of 2 functors, sort of component wise, is just super boring. There is a way that we could also consider the composition to be the product, but I think we have to go to like by categories to get there. So yeah, that's all I got from these notes. Is that enriching for anyone?
Yeah, that was helpful.
All right. So yeah, I think it's the products are sort of an easy thing to think about, and they have this sort of universal property, right? And it's a very accessible universal construction. That is, we can, you know, we can think about this idea that like for any X, you know, we can find a unique thing that makes this work. And this kind of thing actually is going to come up a lot. There are things that are product-like, which are, you know, there are like ends and limits and pullbacks and other things like that, where our intuition for products is going to help us a lot. And then also when we go to co-products, we're going to see more things like this, except the arrows all go the other way, where our intuition for things being sort of free is going to help us. Like the intuition we have for the free monoid, for instance, where like for any other monoid we can fold a list using that monoid. That intuition is going to help us when we look at co-products and co-ends and push outs and things like that. So cool. For next time, so we could look at categories with products and HOM sets. I was thinking we could just go through those 2 things. So 2.6 and 2.7. I don't think those are particularly rich or difficult. So he's just sort of like patching up as an end to this chapter. And then the session following that will go over like 1 or 2 of these exercises. And then we'll get to duality. All right, cool. Anybody else have any thoughts to share? Any concerns, questions?
Yeah, while we were talking about this, I just went off and hunted down what looks like Ed's Haskell realization of products, and I'll paste the link in the Tech Talk Cast channel. I thought that was interesting. He didn't do it quite the way you did it in Haskell. He had some type family, but kind of an interesting thing to look at.
Oh, okay. Cool. That's definitely something to look at. Thanks, Doug.
Yeah.
All right. Anything else? All right.
I don't think so. Thanks a lot, Reno.
Hey, thanks, guys. I'll see you next time.